Dynamic programming is a powerful technique for solving optimization problems in networks. Imagine a traveller who must go from City 1 to City 10 while minimizing travel costs. Each city is connected by routes with different expenses, and the challenge is to find the cheapest path. Instead of recalculating costs for every possible route, dynamic programming breaks the problem into smaller sub-problems. The minimum cost to reach each city. By storing and reusing these results, we avoid redundant work and efficiently build the optimal solution step by step. This approach guarantees the lowest travel cost with systematic precision. To understand more about the problem, consider a person who wants to travel from location 1 to location 10 at minimum cost. The cost of travelling from location I to location J on the connecting lines is shown in the figure below. Before we start, we need to define 7 characteristics of dynamic programming. For the proposed problem of this survey, state N is defined as the number of remaining places. State is defined as the city, I, we are located in. Stage N, action K, is defined as to choose the specific route. Here, policy is described as choosing a specific route from a particular city to a next destination. Moreover, for any action in particular state and stage N, we need to pay a cost, which is stated as follows. A dynamic programming technique is performed using either a backward or forward method. Here, we use the backward method. In other words, the solution starts from City 10, where the trip intends to finish. In each stage, we go one step at a time to previous cities from places 0 to 1, and from 1 to 2, 2 to 3, and finally from 3 to the beginning of the trip. In stage 2, for each state I, we have 2 choices, or actions K. Each action has a cost, and it brings to either node 8 or node 9. And the remaining cost from stage 1 is added from the first table, as shown in the following in detail. The process continues for the k equals 2, and the optimal values are computed based on what is paid in this stage plus the optimal cost from stage 1. After computing all possible cases, we find the optimal cost and place it into F star. Here, K2 is determined from the column the minimum cost was chosen, and K star is determined from the previous table as follows. In stage 3, there are 3 states and also 3 actions. For each action in this state, we need to pay a cost plus the remaining cost, which is associated with the city we end up in by taking the action in this state. For instance, when we are in City 4 and take the first action, the cost in this stage is 4. But we need to add the cost from stage 2, which is 4. Note that here, action 1 and action 2 both give us the same number, so we have multiple options which should be considered in this stage. These multiple options in some problems will lead us to have multiple solutions. Here, the optimal values and multiple choices are stated for state 4, where both yield the same cost of 8 by choosing different routes. And the previous optimal actions are chosen from the previous stage. Note that in dynamic programming, each stage is only connected to the previous stage. Finally, we reach stage 4, which is the first city we actually start the trip. Here there is only one state and 3 actions. We repeat the computations similarly and find the optimal solution. To find the optimal path, we start from City 1 to City 3, which yields the optimal solution. From City 3, we see the other optimal actions, shown in the figure, and find the optimal solution. The following table summarizes the optimal solution, optimal action, and policy in different stages. Here we show the optimal path using a red line from City 1 to City 10. This lecture is provided by the Growing Science publishing firm. We hope you find this useful for your research.